Thanks for having me in this workshop and welcome everyone to my presentation. Today I'm going to talk about a recent research project we did on attacking optical flow using adversarial attacks. And this is joint work with my collaborators, which are both from my research group and Michael Black's group at the Max Planck Institute for Intelligent Systems and the University of Tübingen. Self-driving systems must be robust. That's evident. But to illustrate this a little bit more, let me show you this video from the Carla simulator. We'll show you several driving sequences that have been obtained using agents that we have learned on the Carla self-driving simulator. And self-driving can just be very hard, even in simulation. The vehicle needs to yield to traffic lights and pedestrians in order to drive safely. And there's many things that can go wrong. Not yielding to traffic lights, for example. Or misdetecting reflections as a pedestrian in front of the vehicle and stopping. Or hitting another vehicle. Or leaving the road. Or running over pedestrians, luckily only in the virtual world here. There's several types of robustness that we might look for, but two important types of robustness are robustness to changes of the environment, like training an agent in such an environment and deploying in such an environment, and robustness to tiny imperceptual adversarial perturbations of the image that significantly alter the classification result. Let's first have a brief look at the robustness to the environment. If you train a agent using imitation learning, you train that agent on an offline data set, and that agent will produce the right action for all images that are very close to the images in the data set, but as soon as you deviate a little bit from that data set, the agent will start to fail. Now there's multiple strategies to overcome this problem, and we are presenting two of them here at the CVPR. One of them is, instead of learning a single imitation agent, to learn multiple imitation experts, each of them specifying to a particular situation. That's why we call the approach situational driving. And to optimize the combination of these experts using task-driven policy refinement, using actual rewards from the environment. Another thing you can do is you can use data aggregation. You can iteratively increase your data set using on-policy generated data. By querying the expert for difficult situations. One famous approach in this area is the Geiger approach, but if you apply Geiger to Carla, it doesn't work quite as well. And the reason is that the data set is very biased. Now we show that if you sample the environment more cleverly, you can actually obtain an agent with significantly improved performance. So these were two examples of how robustness to environment could be gained. Now let's turn to the main focus of this talk, which is robustness to these small perturbations of the image. Adversarial attacks already have a quite long history. They were first discovered in 2013 in a paper by Szegedi et al., where they showed that if you take an image and add a tiny perturbation, which is heavily magnified here, to it, resulting in this image, the image that was classified correctly before now gets classified as an ostrich. And not only this image gets classified as ostrich, but also the other two images here get classified as ostrich. Now, how does this attack work? More formally, given a classifier f that maps an image to a set of labels, 1 to L. We want to find an adversarial example for that image. And the adversarial example is x plus some delta x, where the delta x is chosen as the minimizer of all possible delta x, such that applying that delta x to x changes the class label, changes the classifier result, or produces a particular class label like ostrich in this case here on the left. In other words, we want to find the smallest perturbation that changes the outcome of the classifier. And what was quite surprising at the time is that the perturbation can be really, really tiny in order to make the classifier really, really confident that this is an ostrich. This spawned an entire research field on adversarial attacks. For instance, it has been demonstrated that here in the case of self-driving, adversarial attacks can be effective on the task of semantic segmentation. So here's an input image, and this is the result of a state-of-the-art semantic segmentation algorithm. And you can see that if you change the pixels in that image only slightly, you can produce an arbitrary label map, which of course has severe implications on safety in self-driving. But it has also been demonstrated that there might actually be a reason to worry about this too much in the physical world. The physical world meaning that if the patches actually not artificially stick to that image by manipulating the image pixels, but put into the real world by printing the patch and then sticking it on the real object and taking an image of that object. What Forsyth et al. Found is that adversarial perturbation methods applied to stop sign detection only work in carefully chosen situations. And our preliminary experiments show that we might not need to worry about it in many real circumstances, specifically with autonomous vehicles. And the reason for this is that if you print a patch and put it in the real world, also the entire image acquisition process, perspective projection, and the noise that the sensor adds to the image gets added, which then changes again the outcome of the classifier in a way such that the attack becomes less powerful. However, it has been demonstrated shortly after that robust physical real-world attacks are actually possible. And one way to obtain such attacks is by simply not optimizing over the objective as shown before, but optimizing over an expectation over all possible transformations. So these transformations could be 3D transformations of the object or simple 2D transformations like affine transformations of the object or sensor noise. Formally, this means finding the attack patch such that the expectation over all possible transformation of the probability of the wrong class label minus the distance of the transform patch of the attacked and unattacked images is maximized. In other words, the label must be wrong and the distance between the attacked and the unattacked patch must be small over the entire class of transformations, which makes these attacks much more effective in the real physical world. It has also been demonstrated that you can design simple graffiti-like attacks that are very easy to stick to, for instance, the stop sign here, that fool the classifier in a similar way and that therefore are relevant for attacking self-driving systems. Now, all of the attacks I've shown you before are attacks that attack a single image or a single texture. Now, a more powerful idea is to produce a patch that attacks a wide range of images. So in this case, the goal is to optimize for a patch that attacks this image, but many other images at the same time by using both the ART idea, so the idea of expectation of transformations, but also optimizing across many possible target images jointly. And surprisingly, it has shown that this is also possible. So here's an example from the results. You can see the input sequence with a toaster sticker that produces slight likelihood for the toaster. But if you add this adversarial patch, you can completely overcome or turn over the original classification result of the banana. Now, this is particularly relevant for self-driving because these patches are easy to apply in the real world by just attaching a patch to an object. And we are in this work also looking at these patch-based attacks, but for a different type of problem, which is optical flow. Optical flow is different from the previous problems because it is a regression problem, and there hasn't been any results on adversarial attacks of regression problems. So we found it intriguing to look into which optical flow networks can actually be attacked using similar techniques that have been applied to classification models before. Why is optical flow relevant? Well, if you look at a typical self-driving stack, in the first couple of stages of such a self-driving stack, you typically have a low-level perception module that takes the input image or LiDAR scan and produces some intrinsic properties of the scene, such as the depth, 3D geometry, semantic label map, 2D or 3D bounding boxes, instances, road markings, or as what we're interested in here, motion, optical flow. Motion estimation is of course critical for self-driving. Here's an example. This is actually scene flow, so it's 3D motion, adds a stereo component to it. But optical flow is an incremental part of scene flow as well. Here in this case, there's two images taken at 2 consecutive time steps in a video sequence, and the result here is the motion vectors of each of the surface points on that object. And what is important is that this doesn't only allow you to estimate what motion has happened in the past, but by extrapolating, also making predictions about the future. For instance, where this pedestrian is moving in the next second or so. Optical flow describes the 2D pixel motion between 2 frames, as illustrated here in this famous example from Gibson. And optical flow contains information about both the 3D geometry of the scene as well as the 3D motion. Here's an example from the KITTI dataset where the optical flow fields are color-coded. The color indicates the direction of the optical flow, and the saturation indicates the magnitude of the optical flow. What you can see is that objects easily stick out of these optical flow fields. There's multiple approaches to optical flow, and I'd like to now briefly review the 3 different lines of optical flow approaches that are dominating today, because this is important for the analysis that I want to show you later on. The oldest type of optical flow approaches are variational optical flow approaches, where such an energy is minimized with respect to the optical flow field U and V. In this original Horn-Schunck formulation, a brightness term and a flow change term are penalized. So here, the brightness change term measures the difference of the intensity of the pixel at xy at time t and the pixel displaced by the optical flow field U and V at the next time step, and tries to enforce that for the correct optical flow, the pixel intensity is the same. This is the constant brightness assumption. Now, because this alone is insufficient and leads to a degenerate model or degenerate solution, typically regularizers are required. In this case, a simple quadratic regularizer on the flow field that encourages smoothness of the flow. The problem with this type of approaches is that they can only estimate optical flow over very small magnitudes. However, optical flow or pixel motion can be very large, over hundreds of pixels, for instance. In order to cope with large motions, therefore, image pyramids are typically used, where Optical flow is first estimated at small resolution, where the motion can be only small, and then it's upsampled to the next resolution, where at the next resolution the image is warped based on that upsampled flow, such that it becomes already closer to the target image. And then this energy minimization problem is solved, yielding to a refined flow that's again upsampled to the next scale, and where again the image is warped, etc. A second type of optical flow methods that have become popular recently are deep learning-based optical flow methods. The first type are encoder-decoder networks, where simple unit architectures are used or stacked together for regressing optical flow and are trained using massive amounts of supervision, often in the form of synthetic optical flow data, followed by refinement on real optical flow ground truth, for which typically only a smaller amount of data is available. And the third type of approach are spatial pyramid networks that combine the classic ideas of the feature of the image pyramid, in this case using this idea for constructing learning-based feature pyramids, and having an optical flow estimator that is actually learned and not using a variational energy-based type optical flow estimator. So the idea are taken from the literature, from the old methods, but several components have been replaced now with learnable components. So here's an example for an optical flow estimation from the KITTI dataset produced through the FlowNet2 algorithm. As you can see, it's pretty precise. It recovers the sign and the shape of certain objects in the environment. Until 2016, classical variational optical flow methods were state of the art, but since 2016, the leaderboards, for instance the KITTI leaderboard, became dominated by deep learning based methods. However, so far there has been no investigation of the adversarial robustness of these optical flow approaches, and that's what we'd like to look at today. So how can we attack optical flow algorithms? The idea is very simple. Given an image pair from a video sequence, here I'm toggling between the first and the second frame of that sequence, of that pair, FlowNet2 predicts a smooth and reasonable optical flow field, as the one I show here. Now the question is, can we obtain a small attack patch that is around covers around 1% of the pixels in the image or less, such that the results of the optical flow method becomes significantly disturbed, as in this case. Formally, let f of I and I prime, so these are two consecutive frames, denote an optical flow network that produces an optical flow field, and let I denote a dataset of such frame pairs I and I prime. Let further A of I, P, T, and L denote an adversarial attacked image where a patch P has been attached to that image after transforming it by some transformation T and inserting it at location L over that image. Let's go back quickly. So this is an example for this operation where such a patch with parameters P is attached to a particular location in that image. Let further T denote a distribution over affine 2D transformations, and let L denote a uniform distribution over the image domain. The goal in an optical flow attack is then to find a patch P hat such that P hat is the minimizer over all possible patches of the expectation over all image pairs. So we want to find a universal patch here as well that works for any image over all transformations and all locations. So the patch should work at any possible location in the image. And we want to minimize the dot product of the optical flow vectors at every pixel, where the left here is the normalized optical flow vector for the unattacked, the original images, and the right side here is the optical flow vector for the attacked image. In other words, we want to find a patch p hat that reverses the direction of the optical flow with respect to what the network would have produced originally. So let's look at some results. We are considering two settings here. The first is a white box attack. In this setting, we attack each of these networks in separation. We sample the location uniformly within the image. We sample scale from ±5% of the possible scales and rotation from ±10%. And then we optimize on 32,000 unlabeled kitty frames. There is no ground truth for 32,000 unlabeled kitty frames, unfortunately, available. That's why we use the flow predictions as the pseudo ground truth. So we use the predictions of the original optical flow algorithm as pseudo ground truth, which is nice. So we don't need labeled kitty frames. Works with unlabeled frames. And then we learn patches of 4 different sizes. As you can see here, depending on the network architecture, we obtain different patches that attack the network in the most adversarial way. But how well does the attack work? Here we see the quantitative results. We measure the accuracy of the optical flow algorithm by looking at the endpoint arrow. That is the arrow between the optical flow vectors on average. Here are the numbers for the unattacked algorithms, and on the right you can see the results after the attack for a 25 by 25 pixel patch or for a 153 by 153 pixel patch. What you can see is that and this is the relative increase in error. What you can see is that the encoder-decoder architectures are attacked much more severely than the spatial pyramid networks that are attacked almost not. Here are some qualitative results. What you can see is that for these encoder-decoder architectures, these are the first 2 rows here. Here you can see the attacked flow field and the unattacked flow field, and the difference between the two. You can see that the attack region extends significantly beyond this small little patch here in the center. It basically shows you the receptive field of the optical flow algorithm. In contrast, the spatial pyramid networks, by utilizing this inductive bias from the early techniques about the coarse to fine estimation, can actually not be attacked. Or the attacks work much less effectively on these architectures. Here's the result for larger patches. You can see if you increase the patch, then also the results gets affected more significantly. Now we turn to the second type of attack that we consider, which are black box attacks. In this setting, the patch is optimized over several networks. In this case, we take representatives from both lines of algorithms. We take FlowNet2 as a representative for encoder-decoder architectures and PwCnet as a representative for spatial pyramid networks. And on the right, you can see the patch that is recovered from this attack, the patch that is obtained. And then we use this patch to attack all the networks. To make the setup more realistic, we move the patch now as if it was part of the original scene, as if it was actually sticking to an object in the scene. And we do this by taking the ground truth information that comes with the Kitty LiDAR scans. Here are the results. Again, we see that the encoder-decoder architectures here in red are severely affected by the attack, while the spatial pyramid networks and also the original old variational approaches do not suffer from these attacks, indicating their robustness to this type of adversarial attacks. Here are some qualitative results for this attack. You can see the patches stick to this traffic sign here. And you can see that the encoder-decoder architectures are attacked much more severely than the spatial pyramid networks. We have also done an experiment where we have printed that patch, and then we have taken a video to demonstrate that this attack also works in the physical world. Here is the patch in the center, and you can see that the optical flow result is heavily compromised if the patch is visible, but the result is just fine if the person moves in front of the patch. It also works for a moving camera. Here we see the result of the FlowNet2 algorithm when the camera is moved. And here's the same result without the patch. In order to obtain some more insights into these attacks, we have proposed the zero flow test. So what you can do is you can ask, well, what happens when the deep network sees identical images? Or what happens when it sees identical images with the identical attack patch stick to it? Ideally, in both scenarios, the network should output a zero flow field, and the feature maps of the attacked and unattacked images should be similar. Here is the result that we obtain. What you can see on the left is the input, which is a random noise image or a random noise image with the patch. And you can see the visualization of the feature maps, certain feature maps across the network. In this case, the FlowNet-C architecture, the encoder-decoder architecture. What you can observe is that the feature activations are actually not spatially invariant, even without an attack. So it produces spatially invariant features, which is something that's maybe surprising. The deconvolutional layers cause checkerboard artifacts that are sometimes also present in the final results, and the feature maps of the encoder-decoder architectures are very different. So here, between the attacked and the unattacked image, you can see the difference between the attacked and unattacked image of these encoder-decoder architectures, which lead to these strong outliers in the final result. In contrast, while PWCnet also has spatially invariant features and the deconvolution layers cause checkerboard artifacts, it doesn't suffer from this difference. So the attacked and the unattacked feature maps, they look very similar. And while it produces also some errors in the flow field at coarser flow levels, it somehow is able to refine this at finer levels of the pyramid to undo these errors that it originally made in order to produce an optical flow field that is actually more precise. Let me briefly sum up. I've demonstrated that placing a patch in the scene may lead to failure of optical flow networks, as it does for classical adversarial attack classification tasks. I've also shown that the patch attacks are somewhat invariant to translation and small changes in scale and rotation, and that these patch attacks work in the physical world, at least to some extent. One important insight from our analysis is that encoder-decoder architectures like FlowNet-C and FlowNet2 are strongly affected, while spatial pyramid networks like SpyNet and PWCnet are actually quite robust. And classical methods like LDOF and EpicFlow are almost not affected. I've also proposed a zero flow test, which can provide valuable insights into optical flow network architectures. I'd like to thank you for your attention. I want to thank you also our sponsors, and we have a blog if you're interested in our research. I invite you to have a look at our blog. Thanks.